Hi guys. Okay, so in this video, we are going to be learning about covalent bonding that occurs by the sharing of electrons. And this happens in nonmetals. So it's very important first you understand a few things about the nonmetals. Which of the elements in the periodic table, there are about 118 of them, are nonmetals. So it's very important you recognize them. You know the symbols of them, you know where they are placed in the periodic table and what are their properties. So I've summarized this on the screen that the nonmetals are mostly bunched up on the upper right-hand corner of the periodic table. And here you see hydrogen is placed in group 1A because it has only one electron. On the other hand, boron has 3 electrons, so it is in group 3A. Carbon and silicon have 4 valence electrons, they are in group 4A. Nitrogen and phosphorus contain 5 valence electrons, they are in group 5A. And oxygen and sulfur contain 6 valence electrons, they are in group 6A. Then comes the halogens, fluorine, chlorine, bromine, iodine. Each one of these atoms contains 7 electrons. They are in group 7A. And you see the noble gases, helium, neon, argon, krypton, xenon, except for helium, but neon, argon, krypton, xenon contain 8 valence electrons. So they are present in group 8A, and helium contains 2 valence electrons, but because it's a noble gas, so it is placed in the column of 8A. Okay, so this is a basic, placement of the nonmetals in the periodic table. Next is, it's very important you understand the other property which relates to electron affinity and electronegativity. So they mean the same. Electronegativity has been measured, and electron affinity simply means love for the electrons. So this is the reason why the the nonmetals do not give away the electrons; they take in electrons. Okay, so we studied that in the ionic bond formation. The metals give electrons, and the nonmetals take electrons because their electronegativity is very high, and it has been measured on the Linus-Pauling scale. So the highest electronegativity is for fluorine, which is 4.0, and the lowest one is going to be for cesium. So here we see in the trend in the periodic table, there is a decrease in electronegativity in the same column going from top down. But if you move in the periodic table from left to right, you move from left to right, you're going to see an increase in the electronegativity. Okay, so that means that the electrons are attracted to the except for the noble gases, to fluorine, chlorine, bromine, iodine, they pull the electrons towards themselves with great force. Okay, so that was a general basic introduction to nonmetals. Their symbols, you need to know their symbols and their names. Now let's look at the bonding capabilities in the nonmetals. Okay, so group 1A, hydrogen, right, that contains only one electron, so it is only going to make one bond. Group 3A is boron, which contains 3 valence electrons, so it's going to make only 3 bonds. Okay, now group 4A contains 4 valence electrons, so carbon and silicon are going to make 4 bonds. Okay, now comes group 5A. Group 5A, its a trend is a little bit opposite. Group 5A, nitrogen, yes, contains 5 valence electrons, but it is only going to make 3 bonds. Now, the driving force why it is going to make 3 bonds is, or carbon is making 4 bonds and silicon is making 4 bonds, is that it's the octet rule. Okay, so these guys are going to follow the octet. So that is why they will make their bonds in this way. Okay, so nitrogen only has 5 electrons and it needs 3 more to fill the octet. So that's what. Okay, next comes the situation with phosphorus. When phosphorus is following the octet, in other words, it only needs 3 more electrons to fill the octet. It already has 5, so it will make only 3 bonds. So yes, in that situation, phosphorus is following the octet. But phosphorus can defy the octet also. And let me put that in a different color. Phosphorus can defy the octet. So here, phosphorus is defying the octet. So purple color is for or maybe change it to some other nicer color, make it brighter. Okay, so here. So here, phosphorus can defy the octet, okay? Same story with sulfur. When oxygen will follow the octet. Oxygen is in group 6A. It can make 2 bonds, which means that it has 6 electrons already. It needs 2 more electrons to fill the octet. So that's why oxygen will be following the octet, yes. And here is the oxygen, okay? Same is the case. Let's just focus here. Fluorine, chlorine, bromine, iodine have 7 valence electrons. They only need 1 more electron to fill the octet. So that's why they will only make 1 bond. So all these guys which are in this sharp pink color or magenta color, these guys are going to obey the octet. And I need to make this a little bit bigger, pencil right here. Okay, so they obey Octet Rule. Okay, so this is one thing. Next is, on the other hand, we looked at phosphorus can defy the octet. Instead of making 3 bonds, it will make 5 bonds. On the other hand, look at sulfur. Sulfur can make 2 bonds. Yes, it will follow the octet, but there are situations it can defy the octet. And those situations in which it is defying the octet is because of the certain electronic configurations. Okay, and we're going to study that in the next video. In this video, I'm not going to cover that, but sulfur can follow the octet. Okay, next comes as we talked about, the fluorine, chlorine, bromine, iodine. In normal conditions, yes, they are going to follow the octet, but there are situations where chlorine, bromine, iodine can also defy the octet. So when they're defying the octet, then chlorine, bromine, iodine will make 3, 5, and 7 bond. So when it's following the octet, it will only make 1 bond, all these halogens, fluorine, chlorine, bromine, iodine. But chlorine, bromine, iodine can defy the octet in special conditions. So let me just write this down here. Will defy octet. Now, okay, will not follow the octet rule. Okay, so these guys will not follow the octet rule in what conditions? One, when they are connected to a more electronegative element. Okay, so chlorine and bromine, for example, if they bond together, chlorine is more electronegative than bromine. So in that situation, yes, the bromine will define the octet, and they will defy the octet in this arrangement. Similarly, sulfur, if it is combined with a less electronegative element, then it will form only 2 bonds. But there are some situations where sulfur is going to connect to a more electronegative element, such as chlorine or fluorine or oxygen. In that conditions, then it is it will defy the octet. So mostly it is oxygen. A lot of, those oxo anions, the polyatomic ions, which you saw in your previous chapter. So this is usually when they connect with oxygen, in that situation, yes, they can defy the octet. Now look at the other situation here. The group 8A, okay, group 8A is going to make 0 bonds, no bonds at all. That's noble gases, right? But xenon, on the other hand, you can change the reaction conditions and xenon can make 2, 4, and 6 bonds. Xenon is capable of making 2, 4, and 6 bonds, okay? So this is very important. You see these exceptions to the rule, and a lot of it in chemistry also depends on the reaction conditions, okay? So those things. So we see that the elements that defy the octet and the ones that do not defy the octet, and the main thing is when they are connected to either, a more electronegative elements, and mostly, oxygen. Okay, so this is one thing. Next is, look at these examples now. So yes, sulfur, when it is connected to H2S, in that conditions, hydrogen is less electronegative than sulfur. So this is, again, if you look at hydrogen is on the far left-hand side, sulfur is on the right-hand side. So sulfur is more. So you see the trend, there is an increase in electronegativity as you move in the same period from left to right. So we see that sulfur is more electronegative than sulfur is more electronegative than hydrogen, or hydrogen is, in other words, hydrogen is less electronegative than sulfur. So yes, sulfur is making 2 bonds. But look at sulfur and oxygen in sulfur trioxide and sulfate. So we see oxygen is more electronegative than sulfur in both the cases. So in sulfur trioxide, sulfur is making 4 bonds. And in sulfate, sulfur is actually making 6 bonds. So you see, it is defying the octet in that case, in both these cases, this case and this case. Okay, next look at the PCl3. Yes, phosphorus is less electronegative, chlorine is more electronegative. So, and phosphorus is, in normal conditions, phosphorus is, connected to chlorine, and phosphorus will make 3 bonds. So this is normal for phosphorus to make 3 bonds, right? Because this is in group, if you look at it, it is in group 5A. Okay, 5 valence electron, and it needs 3 more, and so it's getting there, and that's fine. But if there is large excess of chlorine, so in that case, phosphorus expands its capabilities. So now phosphorus is making 5 bonds. It's capable of making 5 bonds, and it extends that capability. POCl3, on the other hand, is again 3, 4, 5 bonds. So here phosphorus is making, so again, we are looking at phosphorus as if phosphorus, sulfur, these are the central atoms. They are in the middle. Okay, now let's look at HCl. Hydrogen, less electronegative than chlorine. And in this case, hydrogen only needs to make 1 bond. Chlorine can make only 1 bond. So in this case, the chlorine, let's focus on chlorine. Chlorine is making 1 bond. Okay, but but chlorate. In chlorate, we see that chlorine is making 5 bonds. So you see that chlorine is now defying the octet. So here the octet is being defied, octet is being defied. All right. Now xenon is definitely not following any of the octet rules here. So xenon is making 4 bonds. Technically, xenon has its octet met, so it shouldn't be making, but it is possible to change the reaction conditions. And in that conditions, yes, we can make the noble gas react, in this case, xenon. Okay, and then xenon with 3 oxygens. Xenon with 3 oxygen is making 6 bonds. Okay, so we see that, it's always, some more electronegative element, attaches, and reaction conditions and the capability of the bond, then in those conditions, if it is capable, they do. And why? If all this is because of some electronic configurations. Electronic configuration. And what is this? What is the secret behind that? The little secret here is the presence of 3D and above. So basically it starts with 3D. 3D, the presence of 3D, 3D, like D block, the presence of 3D orbitals, which allow that expansion. Okay, and so then they're able to make more bonds. So okay, now let's look at the covalent bonds or the Lewis structures in diatomic molecules. Now when we say diatomic, what does this mean? Diatomic means di means 2, and atomic is obviously 2 atoms. Now generally these 2 atoms are the same kind. So how are the bonds formed here? So let's first look at everything, it has to boil down. If you look things in the electronic configuration format, you're never going to go wrong. Okay, so here we see hydrogen. Hydrogen has only 1 electron, right? So that's the atomic number for hydrogen is 1. Okay, and where is that 1 electron placed? In 1s1. Okay, now let's put this in the orbital diagram. This is the 1s1 orbital. This is 1s1 orbital, and this one is containing 1 electron, and this one is containing 1 electron. Now, hydrogen does not follow the octet, which is fine, So the you know, there's something else. Did I write this down here? I just want to make sure. So these guys, so let's just put this thing here. Phosphorus, sulfur, chlorine, bromine, iodine, and xenon. So phosphorus, sulfur, chlorine, bromine, iodine, and xenon. These guys defy the octet, okay? So just keep a list here, okay? Now let's go back here. Diatomic molecules. Now here what happens is hydrogen, and oh, sorry, that's what I was thinking. So here we have hydrogen, helium, okay? And then lithium, beryllium, boron. These will not follow. Lithium, just a metal, beryllium, and boron. These guys also do not follow, defy octet. So all these guys are going to defy octet rule, okay? Now, look at this hydrogen now. Hydrogen doesn't follow the octet, so we'll leave that on one side. But now we want to focus on hydrogens internally wishes to be like helium. In other words, hydrogen wants to have 2 electrons and it's going to be happy. Okay, so in that case, this hydrogen and the other hydrogen, they both overlap. So when they overlap, in that case, these electrons can move around in the orbitals of each other. That is what is sharing. Okay, basically it means like when you are basically, you know, you have more room, you are more space, you know, you can just basically, you know, write roommates. So people share that space, you know. So this is the story here, that this is the overlap or these electrons. Then each of the hydrogen gets to keep the you know, the electrons. I mean, can have 2 electrons. So here's another way of showing it. This is the Lewis structure of one hydrogen and the Lewis structure of another hydrogen, the Lewis dot, only one electron. So now what happens is that this hydrogen gets to keep this electron also. So that way it gets 2 electrons and it looks like internally like helium and it's very happy. That's what it wants to look like. Okay. And the other hydrogen is also wanting to have 2 electrons. So then he also gets to share that 1 electron. So now this guy also has 2 electrons. And when it has 2 electrons, so this one also, each one of them is behaving like helium. Okay. So now how do you show this? This is like a single bond. And when it's a single bond, so this then is 2, like H2. So whenever 2 electrons are shared, then single bond. Okay, a single bond is formed. So, and that single bond, now this is equal sharing. This is equal sharing of electron. Okay, so this equal sharing of electron, you know, creates a non-polar bond. So we will talk about polarity, you know, in the next video, but just for now, non-polar means it's the same, you know, equal sharing. Okay, that leads to non-polar. Now let's look at another example. Here we have chlorine. Okay, when chlorine reacts with another chlorine, what happens? So here's the chlorine 17. Okay, so the inner core of chlorine is of neon. So these 10 electrons are of neon. So we keep it like that. 10 electrons are of neon. The outermost electron, these are the valence electrons, and these are the 7 valence electrons. So 7 valence electrons are of chlorine. So where are they placed? So this is where they are. This is the 3s2. This is 3s2, 3p5, 1, 2, 3, 4, and 5. Okay, so that's the orbital diagram of chlorine. Here is 1, 2, and then these are the last valence electrons. So first fill them up singly, always do that, and then you start pairing them. And if, you know, whatever is left, that's fine. Then we focus on the one that is left. And so now we are looking at it, that 3s2 paired, and then the two orbitals from the 3p are paired, but one is unpaired. So it's always the unpaired electron that is needing to be paired, right? And so when this one is needing to be paired, so what's going to happen? They are going to overlap. So these two will, this is going to be, this is the one that is overlapping. So when that overlap happens, so in this case, now chlorine gets 18 electrons, and in this case, it is not going to acquire the negative charge. But internally, each chlorine will have 8 electrons in their last shell. So here is the chlorine with its one electron. Let me just do it here. How do I write this? So let's just put it here. Each of the chlorine internally looks like argon. Argon is 18 electrons, okay? 18 electrons, and that's the noble gas configuration. So internally, it wants to look like a nearest noble gas, and that's what it's looking like by sharing. And then another thing also happens is that when it acquired, so these electrons are, you know, mutually shared. So octet, this chlorine will have, how do I do this? This chlorine will have its octet met, 8 electrons, and this one, the bottom one will also have its octet met, 8 electrons total. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. The top one has 8. The bottom one also has total of 8. Okay, so now how do we show this? How do we show this in the Lewis structure? So we know that chlorine is in group 7. Okay, so when chlorine is in group 7, 7 valence electrons, right? And here is this other chlorine, 1, 2, 3, 4, 5, 6, and 7 valence electrons, right? And now we have 7 valence electrons of each of these, and chlorine internally wants to have 8 so that it can have its octet met. The only way that can happen is if that it gets to share the electron of its other neighbor. Okay, and then this chlorine also gets to share the electron of its neighbor. So this way, each of these chlorines will have 8 electrons, right? And since 2 electrons are involved in this sharing, so chlorine and chlorine are now connected with a single bond. So 2 electrons, and like that, we show the full molecule like that. Okay, and so this thing is Cl2. Okay, and so we talked about 2 electrons is one single bond. And so this bond is a non-polar covalent bond. Non-polar bonds are formed when there is equal sharing. Okay, of electrons, obviously. Okay, let's look at the oxygen now. Oxygen is 8. Oxygen is 8. So now we have oxygen is, now I'm not going to draw the electronic configuration anymore. We are just going to draw the Lewis structure. So here is this oxygen, which is in group 6A. Okay, it has 8 electrons, that's fine, group 6A. So as you see, let's look at the periodic table again. Here is the 6A, group 6A, and oxygen is there. So group 6A means it has got 6 valence electrons. So how are you going to show them? Always put them like in pairs. So 1, 2, 3, 4, 5, 6. Right now it's okay to put them like that. Ideally, you know, best would be to, okay, just do it. So I'm sorry. Okay, here. 1, 2, 3, 4, 5, 6. So this is more like the first one was 90 degrees, the one I initially drew. It's kind of like, you know, initially we start from there, but ideally it is like this spread out. There is more room for them to spread out. Now that's a part of VASPER theory, you know, where these electron clouds they also repel each other. So the maximum they can push each other away is at that angle, which is above 90 degree. I think it's 120. So at that angle, if I'm not mistaken, just check it, 120 or something. So that maximum they can away from each other is obviously more than 90. 90 was more constrained. So anyways, so here's this one oxygen and this guy here. So this is another oxygen. Okay, now what we see here is that this oxygen is going to take these electrons, 2 electrons, because oxygen has 6 valence electrons. Okay, 6 valence electrons, and it needs 2 more to get an octet. And then this is how it gets the octet, when it gets to take the 2 electrons from its neighbor. Next is this oxygen. The neighboring oxygen is also going to do the same. It is also going to get these 2 electrons and this thing, and here we have 8 electrons. All right, so we have these total, like the total number of electrons don't change. It's just the arrangement, the way they, they overlap, or, or separate out, whatever the thing is. So here we have oxygen. Now, since 4 electrons are involved in the bond formation, ideally it is a double bond. So this and this is 1, 2, 3, 4, and then 2, 3, 4. Okay. So this is the structure of oxygen. And once again, since 2 atoms are the same kind, non-polar, equal sharing. Okay. Next, look at nitrogen. Now, nitrogen is in group 5A. Okay. And nitrogen has how many valence electrons? 5 valence electrons. Okay, and nitrogen total is 7, but 5 valence electrons. So let's draw nitrogen. So here's nitrogen, and I'm going to put these 3 valence electrons here, 2 here. And then here's this nitrogen, 3 valence electrons here and 2 here. So now what is happening? They are going to connect. So these 2 are connecting, these 2 are connecting, and these 2 are connecting, means overlapping. But why are they overlapping? Because it has 5 valence electrons. It wants 3 more, so it can have octet. And so when they connect, in other words, when they overlap, so this nitrogen gets to keep these 3 electrons of its neighbor. And same is the story with the other nitrogen also, which is going to take these 3 electrons of its neighbor. And so now we have one nitrogen, 8 electrons. This one also gets to take 8 electrons. So it's obeying the octet rule. That's the reason why they overlap, for that. So internally, it is the electronic configuration. But now you see, and in the electronic configuration, unpaired electrons basically. So here we have the nitrogen, 2 nitrogens overlapping, and 6 electrons are being totally involved. In other words, 3 electrons each is, giving away its 3 electrons to be shared. So 6 electrons, sorry, 6 electrons are involved. So that means it is a triple bond. Okay, and in that case, in this case, the name is, so you can also show it like this: nitrogen, double bond, triple bond, nitrogen, and this is N2. All right. Now the other one on top, I forgot to write, there were 4 electrons were involved in sharing. So this is they form double bond. So 4 electrons in sharing, 4 electrons are being shared. So a double bond is formed in the case of oxygen. So 6 electrons, triple bond, and 2 electrons is a single bond. Okay, now let's look at the rules that relate to the formation of, these low structures when there are more than 2 atoms. Okay, so it's not diatomic, it's more, different types also. So here we see What are the rules? So first is count the total number of valence electrons. So count the total number of valence electrons. That's first thing, everyone, all the valence electrons. That's one thing. Next is identify the central atom. Okay, somebody has to go in the middle. If there are two or more atoms, right? No, sorry, more than two atoms, then, three atoms, somebody has to be in the middle. Okay, next, what is the rule for that? The rule is the ability to make the maximum number of bonds. That atom that has the capability to make the maximum number of bonds gets to be in the center. And the one that has a lower electronegativity, although that's not all the time the case, but the bond formation takes the precedence. So the ones that makes the maximum number of bonds comes in the center, and the one that has a lower electronegativity, that one that comes in the center, because electronegativity is full of the electrons and you want to make a molecule stable. So that's that still is the driving force. Next is connect the central atom and the other atoms with single bond. So now you're going to connect the central atom with outer atoms with a single bond. Next is count all these electrons that got used in single bond formation. Count those. Then subtract the above number, all the electrons that got used up in single bond formation, subtract them from the total valence electrons. Okay, so subtract these from the total valence electrons. Then whatever leftover electrons, what do? You use the remaining electron to fill the octet, if they follow the octet, okay, of the outer atoms. Octet of the outer atoms. Next is the leftover electrons. What do them? The leftover electrons go on the central atom. Any leftover. Now you're going to check for the octet. Is the octet of every atom, if they follow, is it met or not? Next is the need to make the bonds. Is that satisfied or not? Is that need satisfied or not? And if it is not satisfied, then you need to rearrange. Okay, so let's look at these examples here. So first example is carbon dioxide. So let's count the total number of valence electrons first of all. Let me use a blue color now. So total valence electrons. How do you calculate that? There is one carbon here and there are two oxygens here. Okay, so one carbon has 4 valence electrons and oxygen has 6 valence electrons. So a total is how much? 2 oxygens, 2 6 are 12, and 4 coming from carbon. So this comes total to be 16 valence electrons. So this is one type of a test question. Next is, we know then which one is going to identify the central atom, carbon or oxygen. Carbon is less electronegative. So let's just do it here. Carbon, this was step 1. Next step is carbon has electronegativity which is lesser than oxygen. So carbon gets to be in the middle, right? Carbon gets to be in the middle. Besides that, carbon makes 4 bonds and oxygen only makes 2 bonds. Oxygen is only making 2 bonds. So that is why we will have step 3, carbon goes in the middle, one oxygen comes here and the other oxygen comes here. Okay, now what are we doing next? Next is you're going to connect them with the single bond. So here, connect these with the single bond. So in the single bond, remember one single bond uses 2 electrons. So we have used 4 electrons. So now we go back and we look at the 16 minus 4. How many are left? 12 electrons are left. So what are we going to do? We're going to use those 12 electrons and place them on the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the 12 electrons have been used up. Now you're not going to bring anything from outside. Now you're going to coming back into this. So nothing is left over here. So we can't put anything on the central atom, but we're going to check for the octet of each atom. Is it met or not? And the need to make the bonds, is it satisfied or not? So check for the octet. Octet of oxygen is met. If you look at it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All 16 electrons are there, but each oxygen has 8 electrons. This oxygen has 8 electrons, but carbon is not happy because carbon's octet is not met, right? So carbon's, what's happening here? Carbon's octet is not met. Carbon needs to have, like, carbon is just making 2 bonds. Carbon should make 4 bonds. That's the nature of carbon. Oxygen wants to make 2 bonds, but oxygen's octet is met, but its need to make the bond is not satisfied. So we will have to do a rearrangement. And what is rearrangement? This lone pair goes here and this lone pair goes here. So now with that said, we have carbon, oxygen, oxygen, and because those 2 electrons from each oxygen have been used now, so now we have, they come and put here themselves here. Remember, 2 electrons means 1 bond. So now we have 2 bonds, and the remaining, they spread out like this at an angle. So this becomes the structure of carbon dioxide, the Lewis structure of carbon dioxide. Check for the need. For the carbon wants to make 4 bonds, carbon is making 4 bonds. Oxygen wants to make 2 bonds, oxygen is making 2 bonds. The octet of carbon is met. How? 1, 2, 3, 4, 5, 6, 7, 8. So those 8 electrons belong to carbon also. Octet of oxygen is also met. How? 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons this oxygen has. This oxygen has 8 electrons too. 1, 2, 3, 4, 5, 6, 7, 8. So this is a perfectly stable molecule, and this is the right structure of CO2. Okay, so then how do you write the formula? The formula becomes CO2. Okay, so this is how you are going to draw the Lewis structures. Next, let's look at the other one. Let's do this one of carbon tetrachloride. Now here, there is 1 carbon, there are 4 chlorines, and we are going to have scenario here where carbon is bringing 4 electrons and chlorine is 4 chlorine, and each chlorine is bringing 7 electrons. So we have 4 electrons coming from carbon and 7 fours are 28 electrons coming from chlorine, and 28, 30, 32, a total of 32 total valence electrons are 32. Okay, that's one step. Next step is which one is going to be in the center. There are 4 chlorines and 1 carbon. Somebody has to go in the middle. Which one is it going to be? So we see that carbon is less. The electronegativity of carbon is less than the electronegativity of chlorine. Okay, so because of that, carbon is going to be in the middle. And yes, we understand that chlorine can make 1, 3, 5, and 7 bonds. But when chlorine combines only these 3, 5, and 7 bonds, remember, 3, 5, and 7 is only if chlorine is bonded to oxygen. But that's not the case. So this is what is going to be working for us. So chlorine is making 1 bond, and chlorine in this case is making 1 bond because chlorine is attached to carbon, which is less electronegative. But at the same time, this carbon can make 4 bonds. So carbon gets to be in the middle. So this is how you make the decision. Next is the 3rd step, which is just put here carbon and chlorine. Just make sure you put them, at like as far away as possible. So let me just do it in this way. Okay, so here's this chlorine on the top. Here's this carbon. Carbon. Oh my God, I'm so sorry. Looks like I'm getting tired. Here's this chlorine, and here's one chlorine. This is another chlorine, and this is another chlorine. Okay, so best is to put them in the tetrahedral fashion. Okay, now you connect them, and you have connected what? Each of the carbon and the chlorines have been connected with single bonds. Okay, so with that said, how many electrons did we use? 1, 2, 3, 4, 5, 6, 7, 8. So we've used 8. We've used 8 electrons out of 32. So minus 8, how many left? 12 minus 32 minus 8 is 24 electrons. Okay, and one second, I have another, excuse me. Okay, so now we have 24 electrons, and those 24 electrons are going to be placed in the outer atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 electrons have been used up that were remaining, and now we need to check for the the octet. Okay, so you're going to see that chlorine, each of the chlorine has 1, 2, 3, 4, 5, 6, 7, and 8. So each of the chlorine has the octet met. It's the same story with each of them. And so that's a very happy scenario for chlorine. Okay, because chlorine is internally, it's looking like argon. So it's very happy. Now comes carbon. Carbon situation, 1, 2, 3, 4, 5, 6, 7, and 8. So even carbon is following the octet here. So carbon has 8 electrons also. So this is the structure of carbon tetrachloride. Okay, so that's the Lewis structure. Now let's look at the COCl2. So here we see that, let's use another color. Here we see that carbon, there's one carbon, there is one oxygen, and there are 2 chlorines. Okay, now one carbon is giving 4 electrons, one oxygen is giving 6 electrons, and 2 chlorines, each is bringing 7 electrons. So what do you get here? So you have 4 plus 6 plus 7, 2s are 14. So you have 14 electrons coming from chlorine, 6 electrons coming from oxygen, and 7 coming from one chlorine and 7 from another. So we add this up, this you get 6 plus 4, 10 plus 4. So this is 24 electrons. Okay, so this is what? One piece. So total number of valence electrons. Next is, out of these, which one is going to be in the middle? Carbon can make 4 bonds. Oxygen can make 2 bonds. Oxygen is making 2 bonds, and chlorine is, yes, it's combined in these, and there are 2 chlorines. Normally, chlorine will make 1 bond. Normally, okay? So which one is getting the center spot? Obviously, it's carbon, okay? Besides that, carbon has the lowest electronegativity, lower in electronegativity than that of oxygen and chlorine, the electronegativity. So that is why it is going to be in the middle. So here comes carbon, okay? Put oxygen on the top and the 2 chlorines here. And the first step is to connect them with a single bond. Each of these with a single bond, 1, 2, and 3. Okay, so now we have 1, 2, 3, 4, 5, and 6. 6 electrons have been used. So 24 minus 6 is 18. So now we need to place these 18 electrons, and we are going to place them, start with the outer atoms first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So all 18 electrons have been used up. So there's nothing left that we put it on the central atom. So with that said, now what happens? We are going to check for the octet. Very important. So we see that the chlorines, the octet is met, oxygen octet is met, but carbon octet is not met. So carbon is very unhappy. One story. Second thing is chlorine happy with one bond formation, each of the chlorines, but oxygen prefers to always have two bonds. So in that case, what is going to happen, oxygen will give its own lone pairs to carbon and oxygen. In between, those two electrons come. And now comes the better structure of this compound, which is carbon. Here's the chlorine. This is another chlorine. And this is the double bonded oxygen. Okay. And this double bonded oxygen, one second. This is the double bonded oxygen. And these are the lone pairs. These are still there. Okay. So this is the real structure. So carbon now has a octet, 8, octet. So all those double bond means 4 electrons, and then the other 2 from the single bonds. Okay, so this is the Lewis structure. Now let's look at PCl5, PCl3, and we can continue going further. I have a lot of these. Let's look at PCl3 quickly. PCl3 is phosphorus, same thing. Phosphorus is, okay, 1 minute. Okay, phosphorus has 5 valence electrons, 5 electrons from one phosphorus, and 3 electrons coming from chlorines. So 3 electrons times 7. And phosphorus has 1 electron, 5 electrons. So 5 here and 7 threes are 21. So a total of 26 electrons. Okay. So this is one thing. Next is phosphorus is capable of making 3 bonds, but at the same time, phosphorus can make 5 bonds also. Chlorine, on the other hand, can make 1, 3, 5, and 7 bonds. So chlorine can make 1, 3, 5, and 7 bonds. Okay. So with that said, now which one is going to be in the middle? Because 3, 5, and 7 only happens, in a very advanced reaction conditions. So phosphorus is here, and the 3 chlorines are on the sides. Okay, and now you link them, and what do you get? You get 1, 2, 3, 4, 5, 6. So minus 6 electrons. So now you are left with 20 electrons. So where do you put those 20 electrons? First, outer atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And we have 2 more left. Remember, the leftover electrons go on the central atom, right here. You get that? Okay, so here we have the phosphorus making 3 bonds, which is the nature of phosphorus in its normal conditions, which is fine. And it has that 1 lone pair on the top. Okay, so now with that said, that is the, now we were talking about checking. So chlorines, each of the chlorine has the octet met. That's one thing, because, 7 electrons plus 1 more electron that is being shared. So here, these are shared. So each of the chlorines octet is met. Now let's look at phosphorus. So phosphorus has 1, 2, 3, 4, 5, 6, and 7, and 8. So 8 electrons phosphorus has satisfied. Perfect structure. Okay. Next, look at POCl3. Again, 1 phosphorus, 1 oxygen, 3 chlorines. Okay, 3 chlorines times. Phosphorus is now bringing in 5 electrons. Oxygen is giving 6 electrons. Chlorine is bringing in 7 electrons each. So we will have 5 plus 6 plus 7. 7 threes are 21. So 21 plus 6. So we have 21 plus 6 plus, 21 plus 6 plus 5 is 32 electrons. Okay, now these 32 electrons, what do we know? We know phosphorus can make 3 and 5 bonds. Oxygen only makes 2 bonds. Chlorine in normal conditions can make 1 bond, but it is capable of making 3, 5, and 7 bonds also. But we always prefer to stick at the, more common position. So here we have phosphorus in the middle, okay, oxygen on the top. This is one chlorine, this is another chlorine, this is another chlorine. Okay, and now you are going to connect them with the single bond. So here 1, 2, 3, 4, 5, 6, and 7, 8. So 8 electrons have been used up. So 32 minus 8 is 24. So we have 24 electrons left over. Okay, so what do you do with those 24 electrons? Put them on the last atom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, 19, 20, 21, 22, 23, and 24. 24 electrons that were left, total 32, right? So this seems like kind of okay, but if you check, you're going to see that oxygen wants to make double bonds. And when you do the electronic configuration, you're going to see that phosphorus will never make 4 bonds. Phosphorus is never going to make 2 bonds. Phosphorus is always going to make 3 bonds. Or it can make 5 bonds in very specialized conditions. So this looks like a specialized condition. So here we have oxygen wanting to make 2 bonds. It gives away those electrons here. So now we have phosphorus, double bond, oxygen, and these are the single bonded chlorines. Okay, so this is the Lewis structure. So for that, if you look at the octet of the chlorines, that is met. The octet of phosphorus, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So phosphorus, remember, phosphorus can defy octet. And this is an example where it is doing this. Okay. Next is, let's look at methane. So 1 carbon and 4 hydrogens. 1 carbon is 12 and 4 hydrogen is 1. So 12 plus 4, 16. Okay. Now carbon is carbon is more electronegative, but carbon can make 4 bonds and oxygen is going to only make 1 bond. Hydrogen. Hydrogen is making 1 bond. Hydrogen is making 1 bond. Okay. So now we see that, let's get another color here. Here. So we see carbon is in the middle, and 1 hydrogen here, another here, another here, and another here. All right, and so now we connect them. Now, important. So we have 16 electrons. 1, 2, 3, 4, 5, 6, 7. Oh, sorry. I made a mistake here. I'm sorry. Carbon should be 4. That's why I was sorry. So carbon is 4. Sorry, carbon is 4. I don't know where I got that 12. I'm sorry. So here is your 4 electrons, and this is 4. So a total of 8 electrons. Sorry. Okay. So here we have carbon making 4 bonds. I'll just do this again. So here is carbon, carbon in the middle, and hydrogens at an angle, which is a much wider angle. And here is your 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So the octet of carbon is met, and hydrogen does not follow the octet. So hydrogen, we already talked about that. Hydrogen does, sorry, where is it? Doesn't or does not follow the octet. Does not follow the octet. Okay, so therefore no need to place any elements, electrons outside. but hydrogen is each of the hydrogen, like you say, do it. So in other words, each of the hydrogen gets to keep those 2 electrons, right? So hydrogens, in a way, it's neat to look like the nearest noble gas. Helium is also being satisfied. So this is the Lewis dot structure of methane. Now let's look at C2H2. And what happens here is that carbon and hydrogen, and this is another hydrogen, C2H2. Because hydrogen cannot be in the middle, because hydrogen only makes 1 bond. We want that entity to be in the middle that makes the maximum number of bonds. Okay, so here we have this, connect them with the single bond. Oh, first let's get the total electrons. So 2 times 2 for carbon, 2 carbons, and each is bringing 4 electrons. And then there are 2 hydrogens, 2 carbons and 2 hydrogens, each bringing, this is bringing 4 electrons, this is bringing 1. So here you have 2 4s are 8 and 2. So we are looking at 10 electrons. Okay, so that's the total. So when we arrange these multi-center, then carbons, generally gets the center spot, because carbons can make 4 bonds, hydrogens on the side. So now 1, 2, 3, 4, 5, 6. 6 electron got used up, and we are left with 4 more. So where are we going to put those 4 more? 1, 2, 3, and 4. Why do we put it in 4? Because hydrogen is already satisfied. If you look at it, this hydrogen has 2 electrons, and this hydrogen has 2 electrons. Okay, now this carbon has 8 electrons. Which ones are those? 1, 2, 3, 4, 5, 6, 7, 8. Okay, and this carbon also has 8 electrons. Okay, so this is 6 from the left-hand side, and then these 2 from the right-hand side. So the real structure is H, C, triple bond C and H. Okay, so for these type of molecules where it's lots of carbon, hydrogen, put hydrogen and carbon. Carbon's in the middle first. Next is the H2O. Now this one is also defying a few things a little bit. So here is your hydrogen. Hydrogen is, there are 2 hydrogens, each is bringing 1 electron. So we are looking at 2 electrons coming from hydrogen. And here's your 1 oxygen, and that is giving you 6 electrons. So we have 6 electrons coming from oxygen. So we are looking at a total of 8 electrons. Okay, now here's the thing. Oxygen makes 2 bonds, and hydrogen makes only 1 bond. Let me just put this right. Hydrogen makes only 1 bond. Okay, so when it's making only 1 bond, can be in the middle. Oxygen has to go in the middle. So here comes this oxygen. Here is this 1 hydrogen. Here is another hydrogen. Okay, you connect these 2 with a single bond. 1, 2, 3, 4. 4 electrons got used up. So 8 minus 4 electrons is equal to 4 left over. And where are they going to go? On the central atom, because hydrogen, same story, hydrogen does not follow the octet. So there is no need to put the remaining electrons on hydrogen. It doesn't make any sense. The remaining electrons are going to go on oxygen. Fine, oxygen was meeting its octet, but now, meeting its need to make 2 bonds, but now it has octet. So 1, 2, 3, 4, 5, 6, and 7, 8. So 8 electrons. Oxygen has meeting the octet, wants to make 2 bonds, making 2 bonds. Hydrogen wants to make 1 bond, making 1 bond. Okay, so this is the deal with these guys. Next is these 2. We're going to finish this up, and just give me 1 minute. Thank you. All right, so here we have nitrogen. Let's change the color. Nitrogen is one nitrogen, here bringing in 5 electrons, and here you have 3 hydrogens, and that is bringing in 1 electron, and you are going to have 5 and then 8, and then that gives you, oh, sorry, 3, sorry, not 8. So this is 3. So total of 8 electrons. All right, so that's one thing. Second is nitrogen makes 3 bonds and hydrogen makes only 1 bond. So nitrogen gets to be in the middle. So here's your nitrogen. Here's 1 hydrogen, another hydrogen, another hydrogen. All right, now you are going to connect them with a single bond. 1, 2, and 3. How many did you use? 6 electrons. So minus 6 electrons, and you are left with 2 electrons. And where are those 2 electrons going to go? On the central atom, according to the rules. So is the structure complete? Check. So we have 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen has this way 8 electrons, happy and satisfied. Hydrogen will not follow the octet, is having 2 electrons, happy. So this is how we will have ammonia. That's the structure. Okay. Now comes the last one, is the HCN. So 1 electron coming from hydrogen, 1 electron coming from carbon, there's 1 hydrogen, 1 carbon, 1 nitrogen, and let's count the electrons. So 1 electron from hydrogen, 4 electrons from carbon, and 5 electrons coming from nitrogen. So you add these two, this becomes 10 electrons. So we need to place these 10 electrons. And which one is going to go in the middle? So we see that carbon makes 4 bonds, okay? Nitrogen makes 3 bonds and hydrogen only makes 1 bond. So hydrogen is never going to be in the middle. Okay, now we are going to put carbon in the middle, nitrogen here, and hydrogen here. Fine. Next is you connect them with the single bond. So 1 and 2. So 1, 2. All right. So now what do you get here? So we have hydrogen and carbon. Hydrogen's need to make the bond is satisfied, wants to make only 1 bond and wants to have 2 electrons. That's satisfied also. But carbon and hydrogen are definitely not happy because nitrogen wants to make, the nitrogen wants to make 3 bonds and carbon wants to make 4 bonds. So keep that in mind, that need is not met. And we have used 1, 2, 3, 4. So 4 electrons have already been used. We are left with 6 electrons. So where are those going to go? Hydrogen is not following the octet nitrogen. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be the initial state. Now you are going to do a rearrangement. Okay, so with that said, what do we have now? Hydrogen, carbon, nitrogen. Nitrogen wants to make 3 bonds. Carbon wants to make 4 bonds. So basically, this lone pair and this lone pair, like all this rearrangement happens. So let's just do this here. So this lone pair and then this lone pair from nitrogen, this comes in. And so this is how you have a triple bond between carbon and nitrogen, which is fine. Okay, so now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All the 10 electrons have been placed, and we have hydrogen satisfied, wants to have 2 electrons. Carbon is making 4 bonds, 3 on one side and 1 on the other side. And nitrogen wants to make 3 bonds. So that's why we have the octet of every single element made. So this is the basic, introduction, and I did a lot of examples here, pretty much. The rest is all practice, and there are many molecules, so there's plenty of practice that is available. And so we will just follow this steps and just make sure that you make a note of these somewhere. My recommendation is make small notes like index cards so you don't forget anything, especially, you know, where they don't follow the octet. I've seen the students making a mistake where hydrogens, they put all the 8 electrons on the hydrogens. No, stay away from that. Hydrogen doesn't follow the octet, okay? Then just make sure that, you know, there are some elements that are going to defy the octet. So don't force octet on them. So see, you know, where it's needed. Then, you know, so this was the theory. And then it's very important that you recognize, first of all, that which of the elements is more electronegative than the other. And then also make a note of these. You know, these are those which group, this one, which ones are going to defy the octet and which ones are not. Okay, so what are those conditions? So those things. Okay, so it's not that hard, but it's just a matter of practice. But I hope that it was easy, and thank you for watching. Bye-bye.